So the title of this work is Domain Generalization by Rejecting Extreme Augmentation. So before I start the experimentation, I want to thank my co-authors. It's the same co-author, but just changing the first authors, so Hector, Fidel, Eric, and Marco. Thank you for all of the discussion. It was amazing. So I'm going to start with a small motivation. So first of all, the target of this paper is domain generalization, or some kind of like some people call it out of distribution generalization. And the main point for this kind of setup is that you have a target class that you haven't seen during training, and you want to generalize to that. So it's a little bit extreme case of generalization because your test doesn't follow your validation or either training. So you need to find some sort of invariances in those train or validation and just extrapolate to your targets. So something that's like domain. Oh, yeah, I don't know what is this, but yeah, something that domain paper showed us that apparently simple ERM baseline plus a strong random data augmentation is better to kind of like, it's kind of like enough to close the gap between the state-of-the-art result for out of distribution generalization. This is a little bit encouraging result because like we've been working on DG for a long time and kind of like invented a lots of invariance based method or kind of different other method. But apparently simply applying ERM with some sort of data augmentation is super powerful. So we didn't want to change that and kind of like we wanted to see if we can kind of like improve upon that, this kind of like default baseline. So we started from this kind of motivation that as data augmentation getting stronger or in a way wider, intuitively it cover a space of more variation of the image. And since in DG we want to cover some sort of unseen targets, there is a kind of like, probably there's a nice spot that data augmentation, like wider and stronger data augmentation can cover those unseen training, those unseen target data that we haven't saw during training. So that was the main motivation, that we wanted to use even more stronger data augmentation on top of ERM to see if we can improve the already powerful baseline. So we're gonna start by two hypotheses, and throughout the work we're gonna see if this hypothesis works out or not, and then we're gonna provide a resolution for the second hypothesis. So what is the first hypothesis? So the first hypothesis is basically the same thing that I just said. So by increasing the state of data augmentation, we can get even better out of distribution. So I'm just going to rephrase, this is a still hypothesis. Through the paper, I'm going to show that this is actually the case. And then simultaneously, since we are making our data augmentation more aggressive, there is a higher chance that we're going to destroy the semantic of content. And since it's kind of random augmentation, it's kind of like there should be a way to be able to avoid that. And actually, the resolution for the second hypothesis is the main contribution of our work. So we find a way that use even bigger data augmentation, but restricted in a way that only give us kind of meaningful transformations. So first, before kind of like continuing the presentation, let me start by defining what is a strong data augmentation design space. So first of all, there are usually two ways to increase the strength of data augmentation. Either you can stack multiple data augmentation together and just apply them sequentially. This is the thing that random augment or auto augment does. So basically, given that, for example, you already have color transformation, you can just append with sharpness, brightness, auto contrast, and just you apply all of them together. This is one way of making your data augmentation stronger. The other way is like, for each of these transformation, you have a parameter that defines the width of the data augmentation. Here, for example, for color, you can extend your color all the way from -1 to 1. For sure, it is still limited, and they designed it in a way that already give the good in distribution data set, in distribution performance. So we chose the second path because like we found it easier and more intuitive to kind of like extend the strength of data augmentation by just make it wider. For sure, we can just kind of like make it deeper in a way and apply more. But to me, like intuitively, both of those would result in the same way, but the stack would be even a little bit more heavier. So that's why we chose this one. So we propose the new search space for data augmentation. We call it wider. This is something novel, but it's not something like really big. But this is just for the sake of proving our first hypothesis that even a stronger data augmentation can result in better DG. So basically, for the wider space, we extended the range of data augmentation significantly from the previous one. So here, for example, for the color, instead of just going from -1 to 1, we're going to go from -10 to 10. So in the pictures, I'm going to show you how visually it's going to be seen when we apply this kind of like wider data augmentation. So let's go back to the first hypothesis. So we said that maybe a strong data augmentation, even a stronger data augmentation, provides better auto distribution. To be able to test that hypothesis, we got the ERM, simple ERM baseline from domain bed. So domain bed has a kind of 5 different auto distribution data sets. So this ERM is basically the same ERM that Meta already provided using the default search space of data augmentation. So throughout this work, we call this weak. And then we tried, on top of this weak data augmentation, we tried many different search spaces to see what are the effects. And as we can see, auto augment and TA ours means that we are using TA, but using a wider space. It's already providing performance gain compared to rest of this search space. So I just want to add, so as I told you, auto augment uses another way of increasing the strength of data augmentation, since auto augment has a stack of data augmentation, but in our case, we just use the width. So both of those can increase the strength of data augmentation, hence kind of increase the strength of the classifier. So this is just kind of like the empirical proof that okay, a strong data augmentation provides better auto distribution. But simultaneously, a strong data augmentation may also destroy semantic content of the image. So here I kind of like sample images from my data augmentation, and I went through the width, basically went through the strength from the two extreme and kind of like the midpoint. We can see that it's clearly kind of like shown here that at near extremes, we're gonna destroy the full semantic image of those semantic content of those images. So although a strong data augmentation is good, but there should be something better than just naively applying a strong data augmentation. Some of these signals are not really useful during training. So our main contribution is like, how can we resolve this issue? So intuitively, the way that we try to resolve this issue is just by rejecting the extreme augmentation. So the way that we see the problem is like, we have our image. So to be able to create a strong data augmentation, we're going to pipeline it on a stack of 2 augmentation. First, we're going to apply the default augmentation from domain bed. So we call it kind of T-weak. On top of that, we can kind of like, we have 2 options. We're going to apply 2 different variations of the wider data augmentation. So the end result that model is going to see is these 2 versions of the transformation of the same image. So during training, we're going to choose if this wider really breaks the signal, we're going to reject this and go back to the big data augmentation. Basically, if the wider keeps the signal as is, we're going to use it during training. And if it doesn't, we're going to reject it and using the big data augmentation. In a way, our forward passes still sees one image, but then we have a possibility to revert back our kind of like action. Basically, that's why we call it rejecting extreme data augmentation. So in a sense, instead of just learning a new space for data augmentation, we already have a huge space, and we try to just prune some of these transformation from this space. So to be able to do that, we need to find a mechanism to kind of like reject this kind of like extreme data augmentation. We use a student-teacher paradigm, or in a way, fast learner or slow learner paradigm. And the reason that we use that is like, usually the teacher model, which is kind of like the weight averaging version of the classifier. It's more robust to the noise. So we use the teacher model to check if the signals is okay or not, and then use that model to update our student. And at the end, we kind of like weight average our student back to the teacher. So using teacher and student, we designed two different rejection mechanism. Since in the domain generalization, we have an extra label called the domain label, we can just use this meta information, or we can ignore this information, but we just design two different methods based on this kind of meta information. The first one is like uses the student version of the domain classifier as a diversity, because like the student is agile, and kind of like we try to see if it kind of like give us really high training loss, and then concurrently it uses the loss on the teacher version of the domain classifier as a consistency, because if the teacher version of domain classifier give us a really bad loss, in a way it tells us that this image it's breaking the signal, so we should kind of like avoid that. And basically we use the summation of these two loss with the hyperparameter lambda to put a trade-off on how much diversity and how much consistency we want to have. Concurrently, we can apply the same idea, but ignoring the domain metadata. So basically, instead of just using the domain label, we can apply the same exact thing on the label data. So here, again, the teacher version of the classifier, which is our end goal, is the consistency reward. And the student version of the classifier, which is like which is the agile version of the classifier, is our diversity. So we want to have a high loss on the diversity because we want to have a like tougher data augmentation, but the tougher data augmentation shouldn't increase the loss on the teacher because it still needs to keep the signal. So by just combining these two, we made a trade-off to which one we want to have. So as a kind of cartoonish picture, so here the pipeline would be first we apply weak data augmentation, then apply the wider one to make it stronger, then apply our reward function, and then basically based on these weak versus wider, we're gonna have a score, the overall score from our reward. If the overall score, whichever like for example, we kind of compare the two rewards. If the reward for the weaker is bigger than the reward for the wider, we're gonna choose that. But if it's vice versa, we're gonna choose the other one. So in this case, we rejected the wider one because the wider one basically destruct the semantic of the image, and that's why we kept with only the weak one. So here I'm showing the results. So the nice thing about domain vet is you don't need to redo, since you have a kind of like solid and static framework. You don't need to redo all of the baselines, and since all of us following the same protocol, we can rely on the result. So here I took the result from literature and applied many variation of our proposed method and compared with them. The two variations, like either we use the domain data or we use the label data, and the third variation is something that's kind of like it's provided to us as a freebie. Because at the end, since you have a teacher version, you have a student version, you can deploy either of those as your last classifier. When you are working with a label, it's usually more robust to deploy your teacher, whereas you deploy your student. So this kind of teach DCR is the same thing as DCR, but deploy the teacher version instead of just the student version. As we can see, if we ignore the teacher version, we are already filling the gap between the state of the art, which kind of like they are having a really powerful result. The only thing that we are, so this kind of like this method MDSDI, we are really close and we are not significantly better than them. But as soon as we use teacher version of the DCR, we can just easily beat that as well. So here, although this was not the main target of the paper, but here I'm just showing the result on IID. And not only, So one thing that in IID makes sense, like in IID, you shouldn't go to the extreme data augmentation. So the whole thing should get reversed. So if you apply extreme data augmentation, you should get worse IID result. And this is also the case. So if you remember, auto augment was already doing great on the OOD, but this is the last method on IID because like it is destroying the semantic of the image, and this is not something good for IID. But something nice about our method is like it's a good trade-off between both IID and OOD, since we have this kind of rejection mechanism. So we are not only doing good like auto augment on the OOD, but we are also doing good on the IID as well. So this is because of our rejection mechanism. And lastly, there is a paper from Google Brain that tried to kind of like measure the qualify the data augmentation. So they introduced two different definitions. The first definition is affinity or consistency in our case. So affinity says that if you apply data augmentation or validation, your new validation should not be drastically different from your original validation. In a sense, you shouldn't change your distribution. So your data augmentation should be consistent with your validation. In our case, since we don't know the validation, it's a little bit harder, but we can peek into the test data to be able to measure that. The diversity says that your data augmentation should be tough in a way that your training loss during your augmentation should get increased. It means that you are increasing diversity or you are increasing more aggressive data augmentation. So for a variety of search space and mechanism, we basically plot these, calculate these two quantity and just measure it in these graphs. So first of all, let's focus on the out of domain because this is the main target of us. As I told you, since we don't have truly target datasets, so I peeked into the target dataset to be able to measure these. So here we can see that TA wider without rejection is the most diverse and least consistent because like it can go all over the place. And TA wide, it's less diverse, but it's a lot more consistent. And our approaches is something in between. So we are more diverse than default TA, and we are better consistent than the kind of like wider TA. And this is another proof that why our approach is working, because like we are putting a trade-off between diversity and the consistency. The same thing also goes for the in domain, which we saw that we are also good in domain, and because that we are still diverse, but consistent in both of these cases. So yeah, that was the presentation. Thank you for listening. So,
any questions for Masih?
Yeah, go ahead.
We're exhausted. Yeah. But yeah, I have a few. Like, so when you apply augmentation, is it on? So you have a validation set,
yeah,
right? When you're training, you augment also your validation set, or is it just the main training?
No, I don't augment my validation set. Actually, and it could be a way, but I follow the best practice. Usually, the best practice, first of all, the DG, the validation comes from the same thing as the training, so you don't use any unseen data. It is still seen, but part of the training, and you usually don't apply augmentation on the validation. But there is no restriction.
It's perspective. But when you think about it, I mean, the validation set is another side of the training aspect, right? It's part of the design set that you have at your disposal. So no one uses augmentation during validation.
I mean, I suspect that the one reason that you don't apply validation because like you can get overfitted. Because if you select your data augmentation based on your validation and you already apply on that, basically probably you're gonna skip all of those augmentation because like the original validation is the easiest one that you want to choose, and if you make it harder, probably you're not gonna select it at all. So this is one of the possibility, but I've seen some papers that they apply data augmentation and validation, but could be a little bit tricky for at least for model selection.
Yeah, see the point. Yeah, another. Someone else has questions.
Yeah, what kind of reward do you use? The reward.
Sorry?
The reward that you use to see which one, like it's weaker, doing better, or what kind of reward is that?
Oh, so the reward is basically the combination of the consistency and diversity. And we calculate consistency and diversity based on the teacher-student paradigm. For the consistency, we use the loss on the teacher, the same loss. And for diversity, we use the same loss on the student. And the intuition is like a student is more agile. So we want to make it, so we want to have a tough training for a student. But the teacher, since it's a robust version, is the weight average version, needs to still get some feedback from the signal. So that's how we calculate our reward. And then we kind of tune our lambda based on the based on the validation.
So those values of R are using this equation.
Exactly. So these two R's, based on if you use metadata or not, you're gonna create your reward for diversity and reward for consistency. Yeah.
Thank you very much for your great
Yeah,
presentation.
sure.
As far as I know, in doing this, the hyperparameter search space is very important. So they, for example, for PRM, they like train for experiments for a single model or method.
Yeah.
I'm very interested to know what kind of hyperparameter search you follow. Do you have any figure to show the impact of the your method-specific hyperparameters like lambda?
Yeah, I mean, yeah.
Yeah.
So first of all, you're right. I guess Meta spent around 10K on GPU hours to kind of like optimize the hyperparameter. And yeah, there's some figures on the hyperparameter. It's appendix of the paper. I don't have it here, unfortunately. But there is a new paper, not a new paper, but kind of like recent paper called SWOT, that they reduce the space of hyperparameter. For sure, it's not as good as the meta hyperparameter, but they show that with a reduced version, which is lots smaller. So we can do it with the Livia computers as well. I did it as well. So with those, you can get fairly good results that is close to the domain bed initial hyperparameter search. And you can still, because at the end, your question is totally right. DG depends on the model selection hyperparameter search. But this kind of SWOT hyperparameter space is something that's fairly good and fairly easy to obtain. And I basically use them. So they only optimize learning rates and they fix the bag size. So if I want to go into details, Facebook for every model randomly change the seed, optimize the hyperparameter, and combine all of those. So here they fix one seed, optimize the hyperparameter, and then after getting the optimized hyperparameter, they ran it for multiple seeds. For sure, you're gonna have a lot more bias using this method, but so far it seems that it's kind of like for some other method, it's doing something, it's doing good. So you don't need that huge kind of hyperparameter search that Meta already proposed that initially. So we use that. Yeah.
Did you first thank you for
Yeah, sure.
Did you test the rejection ratio in epochs? I mean that based on curriculum learning, maybe at the first training epochs, maybe the rejection ratio may be high, and after the model converts and more. And did you test this rejection ratio between epochs, and also did you test at the curriculum learning maybe fit their wider augmentation at the end of training?
Yeah. So yeah, that's a right thing to say. I still don't know. So intuitively, curriculum learning is good and it should improve, but in practice, I'm not sure if I'm the only one. Like I cannot make it work. Probably it's because of the hyperparameter. Yeah, my intuition says also the same thing as you suggested, that initially we need to have kind of like less aggressive data augmentation, and throughout the training, toward the end of the training, we need to make the width or kind of a strength bigger and bigger. But I guess it depends a lot on the model you are using on a data set, like where are the kind of those critical points. So I tried many things and I couldn't make the curriculum learning works. And at the end, whatever I do, random is the best. And that's why we build our method based on the random data augmentation. Like the initial idea was to search and find kind of like learn this search space, but whatever I did, I couldn't beat the random. So I guess this is the same thing for the curriculum learning. you can try to find a critical point where you kind of like extend your bit, but this is only a case specific for one data set for one model. At the end, for the big picture, probably random gonna beat all of those. But I still have hope on this kind of like approach, but I couldn't make it work. But there is one figure in the paper that shows it's not honestly curriculum learning, but it shows that our rejection rate is based on the target data set. So for example, if your target data set is more aggressive, the rejection rate would be less. And if your target rate is more aggressive and the rejection, no, if your target rate is kind of, if your target domain is really different from training, the rejection rate would be less because you want to have more variety. But if your target is really close, your rejection would be higher because you want to keep your model more consistent. But yeah, I tried curriculum learning, but I failed.
And also, did you, for each input for training model, you created 2 versions of augmented?
For each batch, basically. So I put it in my data loader. So each...
No, I mean that at the same time you feed the original augment and wider augment.
But I don't update. I just feed it to calculate the reward, but then reject one of those and then update my model. So it's not like I'm applying forward on 2 models. So all the time my update is happening one, like it's like the old, like the simple ERM. Only the model sees one version of the augmented version. But I apply forward passes in a kind of like no gradient setting just to calculate reward.
So there are 3 questions online. I don't know if you want me to read them or if you want to open the chat. You from Dan and one from Hassan.
Where is the chat?
Right there.
Oh, yeah.
Hi, Masih. I can actually read the question for you. So my first question is, why do you get such a better performance with the teacher in your results?
So we have some hypotheses. So first of all, using a teacher to get a better result is not something novel. So there are already few works that they say that if you use the kind of like weight average version of the classifier, you're gonna get better results. And they relate this to some sort of ensemble, because like since you're in the pre-training regime, you are in a way doing ensemble, and your ensemble are weight averageable. So since your ensemble are kind of like close in the weighted space, you can just collapse them into one model. So one reason behind the good result of teach version of our method is because of we have different checkpoints. And the other thing is, like, I guess at the end, teacher is the more robust version of the classifier, and we're going to ignore the noise because we are kind of like using the slower weight update than the students. So these are the 2 things that I can think of about the better result for the teach version of our kind of like proposed method.
Okay, thank you. And I have a second question. The transformations that you're using, they're mostly geometric transformations, right? Like translation, rotation, cropping?
Actually, no. So here we are using brightness, auto contrast. So we have a variety of color-based transformation as well. So we have posterized, solarized, color, contrast, sharpness, bright. So all of these that you can see here is also included in our search space.
Okay, but like I was wondering, like if you, let's say, want to be robust to extreme domain shifts, like let's say going from a natural image to a sketch.
Yeah.
How would these transformations, let's say, allow you to create an image that would look like a sketch from a natural image, for example?
Yeah, actually, that's a good question, and this is something I kind of like skeptical because domain bed introduces these data sets, but these data sets are synthetic. Like, I'm not sure in reality one would train on the natural images and then try to go to the sketch images. But anyway, this is the case for domain bed and everybody is using that. but I can think of some combination of these that can help at least. When we see the sketch images, mostly the background are white, and you kind of like have the stroke of the pen. So maybe by just changing the color and just changing the contrast, we can make it similar to that. But I totally agree with you. I don't think there is, using this kind of like computer vision based data augmentation, there is no way we can change we can apply this sort of transformation and just jump from natural images to stroke images. There is no way. Like the thing that we can do is to be at least close to them. I guess for those, we need more generative methods for transformation. But I mean, we follow this search space because this is usually the search space that people follow in the literature. But for the extreme domain shift, I guess these are limited because like there's so much you can do with this.
All right. Well, thanks, Masih, and congrats for the paper.
Yeah, thank you.
There's another question online by Ehsan. I don't know if Ehsan, you wanted to speak yourself, or you want us to read the question out?
Oh,
so it's about.
Did you apply any contrast?
Hi, everybody. Thanks for your presentation, Masih, and congratulations on your paper. I just wondered that did you apply any contrastive learning strategy on weak and rejected wider augmentation as positive and negative samples to improve the latent space or not?
Oh, no. We didn't do any kind of like self-supervised or kind of like pre-training on those images. We just straightforward do the supervised learning and reject or accept during training. I mean, it's an interesting approach, but no, we didn't try it.
Future consideration.
Yeah.
Thanks.
Okay. Are there any other questions online or in the room? Oh.
Check if the rejected augmentation are the same for every image. For example, one kind of image and another kind of image will have a very different rejected augmentation.
Honestly, no, but I have a graph in the paper that, as I was telling Mandy, I have a graph in the paper that shows the number of rejection. But no, other than that, I never peeked into visual aspect of the images per kind of like per domain.
Do you think it really depends on the input image, or rejected augmentation would be the same for every kind of image?
I mean, to me, it's at least the least thing it needs to be depends in your training domain. So, for example, if you have so sometimes it's possible. The way that we do DG is like we left out one domain as target and train on the rest of the domain. Sometimes the target domain is by luck is really close to the train domain. So in that scenario, your rejection probably is more similar because like all of those domains are close together. So by chance, kind of by luck, that target domain can gain. But if you have kind of like your target domain as a sketch, then there is nothing representative in your training. So like the best you can do is just to be more as aggressive as possible.
And how about the graph with the diversity?
Yeah.
Versus I don't remember.
Yeah, the last graph. Okay.
So your point in between two extremes. Could you maybe it would be best to be on the top right corner?
On the it would be best. Yeah, but to be able, like, I'm not sure if it's even like for sure it's the best to be on that, but it's kind of impossible to make it really diverse but still be consistent.
Do you think you can maybe regress what kind of augmentation rules you should have just looking at this graph?
I'm not sure
like,
if
the set of augmentation rules that are allowed would put your point in between those two extremes.
So one thing that we can conclude is like, first of all, for good DG, you need to make your, so far, all of the literature follows auto-augment and rand-augment, and they are already designed, even the station space, to be good on in-domain data, so like cipher, images, and everything. So first of all, we need to leave that assumption, because for DG, we need even more extreme one. Okay, so now that we have this assumption, so we need to find a way to make our space smaller. So rejection is one way, but maybe there are possible other ways. So as a kind of to answer your question, first we need to make it as diverse as possible to be in this kind of like area, and then make it closer and closer and closer to the right side of that table. I guess this is the easiest path to kind of like reach that. First, make it diverse, and then somehow make it more consistent, either through rejection that we propose or through some other mechanism.
Any more questions?
For wider augmentation, did you use bigger sigma for normal distribution or bigger range for uniform?
Yeah.
And did you test the cases with rejection normally occurs in the wider or in the middle? Because you use random, maybe the wider augmentation without rejection occurs in the middle at the same as with augmentation.
Yeah. Yeah, that's really good question. Again, unfortunately, I haven't peeked into the visualization that much, but when I was debugging my code, I saw that there are some for sure examples that are gonna get rejected. So for example, in this, so these images are kind of like easily can get rejected because there is no enough signal. But these images, one can argue that these images are rare because like these are at the two extremes. So other than these, what kind of like rejection we're gonna see? Honestly, I haven't looked into visualization. That's something important that I need to look. But my search space is really big enough that even these extreme one is not that kind of extreme. That's kind of like unlikely. For example, for the color, it goes from -10 to +10. So there are lots of space that you can get absolutely black images. So it's not really kind of unlikely to hit that spot, but for some other transformation, it's really unlikely to hit that extreme. And during sampling, you may not kind of like occur that kind of like augmentation, but for sure there are some transformation that it's not that kind of unlikely to hit the extreme. And to answer your first question, I use the PyTorch implementation. In PyTorch, I guess they use only uniform. So I just expanded the uniform to make it wider. So from -1 to -10 to 10.
One nice solution for that, maybe in the reward formulation, estimate the base rate of augmentation and incorporate that number or score in your reward function.
Oh yeah, that's nice. The only issue is like, so there are some engineering aspect that kind of like I had a struggle with. So to be able to make it fast, I had to incorporate this kind of like data augmentation in the data loader to make it multi-process. If I don't do that, I need to do everything on GPU and everything kind of like during my forward pass. It will be super slow, but that's where all of those shiny things can.
No, I mean, if your implementation, you can use some transformation as a parametric transformation. In the PyTorch, you can, before the applying, you get the parameter, random parameters, and preserve that parameter.
Oh, I see. And then update those only.
Yeah. Before the applying, you can get the random. For example, for segmentation augmentation, you need to apply the augmentation as well as labels.
I see. Okay.
You need to some parameters to have the same augmentation for also current use. But I mean that, or maybe remove the center for uniform area.
I see.
And
in the beginning, I had, because like I wanted to test this, kind of validate this hypothesis. So I had a space that kind of like removed the midpoint to make sure that if it's really effective. I didn't put it in the paper because it was at the beginning of the whole project, and it was promising. So basically, if I remove the midpoint, the rejection, if I remove the midpoint, then there's a higher chance to go to the extreme. And even in those cases, rejection was working, because then it would go less towards the extreme point and only kind of accept the one that is less closer to the extreme point. I totally agree with you. Probably it would be really good ablations to have that inside the paper. I remember that I had at some point, but I don't know why I decided not to put in the paper. But yeah, it was one of the motivation that I kind of like encouraged me to go through the rejection schema.
Yes. Okay, so thanks for the questions. We have one from Marco, and maybe we can end on that.
Yeah. Okay.
Yeah. Can you hear me?
Yeah.
Okay. Can you go to the slide of IID in domain?
Yeah. Okay.
So
this slide?
yeah. I wonder why in domain auto-augment performs so bad, because in theory it was built for in domain data augmentation, right?
Yeah, I mean, I have some hypotheses. I'm not sure I'm fully correct, but first of all, auto augment trained on image nets, and then they freezes the data augmentation and then use it for any other data set. So it's not optimized for all of the data sets. And there are already paper shows that auto augment sometimes applying really aggressive data augmentation. So I still believe that auto augment is like wider version of our search space, because auto augment uses, I guess, a stack of 3 data augmentation. And although each of those data augmentation are narrow, but a stack of those 3 can give you really kind of like drastic result, at least in some data sets. But I guess this is because of that. I'm not sure if it's true generally, but I guess at least on the domain data sets, it's not going to work out of the box from the ImageNet.
Okay, thanks. And congrats.
Thank you.
Thanks everyone for coming and having great questions, and thanks again to the speakers. Great job.
Thank you.
They're both in the lab, and if you feel like continuing to provide comments, hope you do. So that's it for today. Stay posted. We have some great talks from now till Christmas, and then of course the Christmas party. And so I hope you come back next time as well.
Thank you.
Thanks.
Goodbye, people from Zoom.
Goodbye.